It is my pleasure to introduce Paul Smaldino. He is an assistant professor in cognitive information sciences. He got his degree at Davis in psychobiology, right? Worked with Jeff Schenk as a PhD student. He's done a couple of different postdocs, Johns Hopkins, back at Davis, a couple of different departments in Davis. Paul Smaldino is like a model of interdisciplinarity, I would say. I mean, you like covered all, psychobiology, psychology, political science, economics, computer science. Well, I'm sure I'm missing some stuff. Social sciences in general. Anthropology, I knew it, anthropology. So really, I think an excellent model for interdisciplinary in general and for the NRT in particular. You probably maybe already know, that's the sort of areas that he's worked in. I would say your specialty is in agent-based modeling, other types of modeling applied to social processes, political processes, evolutionary processes, economic processes. And today he's going to be telling us about taking that perspective and applying it to science as a process. So join me in welcoming Paul Smaldino.
Yeah, it's really happy to be here today and to talk about this is a sort of ongoing project. As Chris said, I have interests in a lot of things related to the interaction between social structure and individual behavior, network formation, and social and cultural evolution. But today I want to specifically talk about how all those things can help us learn a little bit about what's going on in science and sort of the culture of science. So last year I went to the March for Science in the spring. Some of you may have gone. This was a really popular poster. I saw many, a lot of different versions of this and online in different cities. People had this. People love this quote by Neil deGrasse Tyson. The good thing about science is that it's true whether or not you believe it. Counterpoint. Right? Not all science is true, right? This was a paper that came out in 2012 where Amgen, the biotech company, tried to replicate 53 landmark studies in oncology, and 47 of them failed to replicate. In psychology, many of you have seen this. This was a big paper that came out in 2015 by the Open Science Collaboration, where they replicated 100 published in top journal studies in psychology, and 61% of them failed to replicate. Exactly what that number is can change depending on what you consider to be a successful replication. But for those of you who know about p-values, these are two violin plots. This is the violin plot of the distribution of p-values of the original published studies, and this is the violin plot of the replications, with that dashed line being 0.05. Neuroscience. This came out last year in PNAS. A very popular statistical piece of software was discovered to contain an error leading to up to 70% false positives for any study that used that method. And this is just some examples, right? Almost every field has some version of this. This was a survey that came out in Nature last year asking scientists, have you failed to reproduce an experiment, either your own or someone else's? Most people say yes. And this is a really big problem. And I think one of the best layouts of why this is a big problem comes from Charlie Darwin over here. This is from The Descent of Man. And he wrote, "False facts are highly injurious to the progress of science, for they often endure long. False views, if supported by some evidence, do little harm, for everyone takes a salutary pleasure in proving their falseness, and when this is done, one path toward error is closed and the road to truth is often at the same time opened." It's very kind of flowery language that Darwin was very fond of. What this really means is false theories are not that big a deal, because if someone has a false theory, a theory that's no good, scientists love showing that other people's theories are crap and their own theories are better. And so false theories are not that big a deal because people will keep trying to come up with better explanations for data. But if we have false facts, if the data we're trying to explain are wrong, then we're going to spend all our time trying to explain things that aren't even true. So this can create a really big problem for science. We can think of sort of science, or at least one kind of science, as a sort of signal detection for facts, right? It would be nice if we could just have a question and then learn it and then be like, all right, that's what it is, right? But it's not that easy because we're looking at noisy signals. Sometimes we get false positives, sometimes we get false negatives. So how should we think about this process, right? This is a sort of kind of folk model of what science is about, right? That there are hypotheses, and those hypotheses are actually correct or not correct, true or false. Then, through some methodology we can try to learn about whether or not our hypothesis is actually true, and sometimes we'll be right and sometimes we'll be wrong. There's two kinds of errors, right? There's the false positive, a type 1 error, or a type 2 error, or false negative, right? But we get results, and the probability of a result is of different kinds is usually denoted by this alpha and beta. I just want to consider this kind of model of science for a second. And so this is a sort of classic kind of question that one might ask. As scientists, this is often originally applied to medical researchers, but I think it's just as applicable to science more generally. So here's the question. Assume you have some method and some test, and that the probability that you get a false positive is 5%. So if the hypothesis is actually false, the probability that you will nevertheless get a positive result is 5%. And then the probability of a true positive finding, this is sometimes called the power, is 50%. So if the hypothesis is correct, you will get a positive result of 50%. Because sometimes you just may miss things in the data. So your test yields a positive result. What is the probability that this finding indicates a true hypothesis? Anyone want to venture a guess? Okay. That's wise that you guys are staying quiet. Okay. The most common answer when you ask researchers is 95%, or at least it used to be 20 years ago. Because okay, well, I got a positive result, so I don't have to worry about power. False positives, 5% chance of a false positive, it's a positive result, so 5% false, 95% true. That's pretty good. But it's a trick question, right? Because we actually know exactly how to calculate this number, right? This Bayes' theorem. And you may notice that there is a term in there that I didn't give you. Right? This is sometimes called the base rate. This is the a priori probability that any hypothesis is true. Before you get your data, this is the background probability that you were right. And if you don't know this, then you have no idea how good your finding is. So let's look at an example. Let's say I have 100 hypotheses I'm testing. So let's say, an example might be like, let's say I have a gene array, and I'm looking at, I'm trying to find a gene that's linked to some mental disorder, and I'm testing 100 different genes. And 10 of them are actually linked to the disorder, and 90 of them aren't. And so I have my 50% power and 5% false positive rate. I test every single one. Well, 50% of the true ones will come up positive, and 5% of the false ones will come up positive. And so posterior probability that this positive result indicates a true hypothesis is 50%. It's a coin flip. Right? It's much worse than 95%. Now obviously exactly this number depends on what the base rate is, what the false positive rate is, and what the power is. And the issue here is that the positive and negative results are all we actually know. We don't know going in what's true and what's false. All we have is the result. So we want to make sure that our results are really good. So this maybe calls for an update of how we think about doing science. So instead of just thinking about it at the point of doing the test, we should think about it as a more dynamic process. So this is a figure from an earlier paper I did with Richard McElreath. We should think about this as a population process, right? And so I'll walk you through this for a second. So starting out with the process of hypothesis selection. this is where the base rate comes in. How good we are at choosing hypotheses is a really important part of lowering the proportion of false positives in the literature. Right? So here in this diagram, the little circles are hypotheses, the red ones are false and the green ones are true, and there's a gray ring around them indicating that we actually have no idea what they are before we test them. Then there's the process of investigation, which I went through. Then there's the process of communication, right? Because when we communicate results, we don't tell everybody everything we did. Not every result gets published. Some things are easier to publish than others. Novel, positive results are generally easier to publish than saying, I tried something and it didn't work. The things that get communicated go into a sort of batch of tested hypotheses. This is basically the scientific literature, and they can accumulate records. Right? They accumulated history of true and positive and negative results. And that's what we have access to. And those things then can be subject to replications and repeated testing. Right? And those things can either be published or not. And what we know is what's in the literature. So then the question can be, based on the literature and assumptions we make about how good we are about testing hypotheses or choosing hypotheses, how strong our tests are power-wise and false positive-wise, what the communication biases are, we can think about given a history of hypothesis in the literature, what is the chance that it's actually right? And we can do this by using a series of nasty equations and plot a bunch of things. So in all these graphs, the y-axis is the proportion of hypotheses which a given history that are true. And here the history is simplified as just the net number of positive findings in the literature. So number of positive findings minus the number of negative findings that are in the literature. And each line is a different number, is a different tally. So I'm just going to ignore most of those things and focus on the ones with the strongest results, the sort of the steepest slopes. And this is maybe not that surprising that the base rate and the false positive rate are the most important things. So if your base rate is really high, if most hypotheses you test are true, then getting a positive result is great, and you should be, we can be really confident. But if the base rate of the hypotheses we're testing is low, if most of the hypotheses we test are wrong, and you should remember that when you're working with data, every single association you test is a hypothesis. Right? If you're just sweeping through all of your data looking for positive results, you're going to get a lot of false positives. The other thing, though, is false positive rate, right? If your test is weak, if it's noisy, if you have a very small sample size, you're going to have a lot of false positives, right? And in that case, you're going to need more positive results, more positive replications to have any degree of certainty in your result. So, okay, what things contribute to base rate being low and false positive rate being high? When are false facts more common? So they're more common when studies are underpowered. So you want to make sure you have a large enough sample, given whatever your effect size is, to make sure that you don't have ambiguous results. We want to make sure that negative results can get published as much as possible, right? Because otherwise we get a skewed view of what the number of findings are. This distorts the literature. There's a widespread misunderstanding of statistical techniques, right? This leads to false positives and ambiguous results, and people think that their results mean that they're right and it's really not the case, or they use the wrong statistical test, etc. And also when surprising, easily understood results are easiest to publish. So surprising results are really exciting, right? There's a wow factor. This I didn't know. Nobody thought that this was the case. This is amazing. But we have strong priors for a reason, especially for working scientists, right? If something goes against all of accepted wisdom, maybe it's amazing and a new thing, but more often than not, it's going to be wrong. Right? And so if there's selection for these kinds of results, that's going to lead to more false positives. The thing about these is we already know all these. Nothing here is new. we've known all of these things contribute to false positives for a long time. So why isn't science better? Why aren't we better at avoiding these problems? And the hypothesis that I'm going to propose is that incentives are not aligned with best practices, and this is a big part of it. So some of you may have seen this graph before. I apologized for there's going to be a big portion of the rest of this talk that's going to be a big bummer. So I apologize. I'll try to bring it back at the end. Right? The gray lines here, or the beige lines here, are the annual and cumulative numbers of faculty positions posted every year in the sciences. And the blue lines are the annual and cumulative number of new PhDs awarded every year. And they're on, the cumulative and annual ones are on different scales, but it's pretty clear that the number of new PhDs awarded is going way up, and the number of jobs is being pretty constant. So we have more and more people competing for about the same amount of jobs. And there's been many articles complaining about this, not so much action on it. So this is a highly competitive issue. There's a lot of people vying for a limited number of spots. What's going to happen? Right? This was an editorial in The Lancet in 2015. This is the editor of The Lancet, which is, if you don't know, is one of the very top medical journals. He said, part of the problem is that no one is incentivized to be right. Instead, scientists are incentivized to be productive and innovative. And so, providing some evidence here, successful scientists are publishing more. So, this is a graph from CNRS, which is a major French research institute, and the y-axis here is the number of published articles that new PIs have at the time of hiring from 2004 to 2013, and it's been increasing. A big factor here is more time generally spent in postdocs, as giving them more time to publish, but also reflecting the fact that it's becoming more and more competitive. One way to get more publications is to produce more papers. And one way to get on more papers is to get your name on a big paper. And this is going way up. So this top graph here is the number of total publications in 4 different subfields of biology over time from, I think, the 1970s to today. And here is the proportion of those that are single author in all those fields over time. So lots and lots more papers, fewer and fewer of them are single authors, more and more multi-author papers. The same as in physics. This is their data goes way back to the 1800s, but this is the proportion of physics papers that are multi-author over time, and it's been increasing. This was a nice paper that came out of Current Biology, doing machine learning on something like 100,000 scientists, or no, that's impossible. Thousands of scientists, tens of thousands or hundreds of thousands of papers, looking at, from start of career to up to 10 years past, which people became PIs and which people dropped out of academia. And on average, the people that became PIs published more papers a year, and they published in higher impact journals. I'm gonna pause for a sec here, because to some extent, right, this seems like it's not a terrible thing. We want to reward scientists who are productive, who don't, waste their time, who actually produce work, and we want to reward people who are influential, who make an impact in their field. So it seems like rewarding publications and impact shouldn't necessarily be a terrible thing. The problem is that these are proxy measures and they don't line up exactly with what we're actually trying to incentivize. And this problem was identified in the 1970s by Donald Campbell and others, but I like Campbell's phrasing of it. He noted that the more any quantitative social indicator is used for social decision making, the more subject it will be to corruption pressures, and the more apt it will be to distort and corrupt the social processes it is intended to monitor, sometimes called Campbell's law. So we can look for this kind of thing. Okay? So I just added this slide today because I just noted this recently. Publishing can really directly lead to some kinds of success. Not so much in the US. But in certain countries, there are direct cash incentives for publishing in high-impact journals. So this is data, this is China. In China, if you are the first author of a paper that appears in PLOS One, and this is data from 2016, you get $984. That's pretty good. It almost covers the article publishing fee.
The government? Who's paying that?
This is the government.
The government, not any particular university.
Yeah, I believe if it may be some sort of collaboration between the government and the universities, but I believe it is nationwide. So not bad. PNAS, 3,513. It's pretty good. Nature or Science, $43,000. Yeah, that's legit. That's a really strong incentive to publish, to get a paper in science. Other countries also provide these kinds of incentives. So here's a partial list: India, Malaysia, Korea, Turkey, Venezuela, Chile. Some countries in Europe don't reward this stuff with cash, but they do make it prerequisites for career advancement, which is almost as bad. So there was a study that came out about 6 years ago looking at what goes on in countries that institute these kinds of incentives. So this came out in Science, and they were specifically looking at submissions to science. So this is relative to 2000 for the rate of submissions to science from these different countries. What is the rate? How did that rate change over time of number of papers submitted to science in different categories of country? So the gray line is no policy change. The green line is the one to look at. Those are countries which, since 2000, instituted cash bonuses for getting a paper in sciences. And you can see that they had about a threefold increase in the number of papers submitted to science, right? Because you get $40,000 if you're Chinese and you get a paper in science. Let's see how this affects, we can look at how this affects the kind of papers that come out. Right? I love this paper. It was from the Christmas issue of the British Medical Journal, which is always kind of a fun paper. This was looking at relative increases in word frequencies in PubMed abstracts since the 1970s. And see that the word amazing had a 1,500% increase. Groundbreaking and innovative both had 2,500% increases. Novel had increased 4,000%, and unprecedented 5,000%. So, I mean, let's be fair, there's two possible explanations for this. One is that studies since the 1970s are 40 times more novel, and 25 times more innovative than they were in the 70s. That's one possibility. The other is that scientists are responding to incentives. So obviously this is bad because such a system can and does incentivize cheaters, right? So in all fields. And so these are just some high-profile cases that came out in the last number of years. So here's a physicist, Jan Schoen, was a superstar, had all these papers in Nature, Science, particle physicist, shown totally fabricating his data. Derek Staple was a social psychologist. They're amazing. When he was found out, it turns out he literally would take his surveys and throw them in the dumpster and then go home and enter the data that he thought he should get. It's nuts. This is the last one is a really interesting case from the British Journal of Clinical Pharmacology, where this is an editorial and the editors are reporting how they discovered this piece of fraud. It's really interesting paper. What the authors, the fraudulent authors had done was to submit their paper and then submit suggested referees, as you do. And they had submitted the names of fairly high-profile people in the field, but then provided fake email addresses that went back to themselves. And so they had reviewed their own papers, pretending to be famous scientists in their field. And they were like, this is fabulous. You should definitely publish this. So yeah, this is a big problem. But I do think like this definitely happens.
Don't get any ideas.
Don't do this. Don't do that. So I want to say this definitely happens. And these guys were caught though, right? And their careers ruined, so be advised. But I think that the vast majority of scientists aren't trying to commit fraud. The problem is that it doesn't require anyone to cheat for this incentive system to be damaging. To show how this works, I present an agent-based model, an evolutionary model of science, sort of a cultural evolutionary idea. So the model basically works like this. And this is from the paper that some of you may have read. There's a population of N labs. Each lab has a characteristic methodological power, so how good it is at finding true results. Increasing the power also increases false positives, unless effort is exerted. So you can imagine it's very easy to have perfect 100% power if you just declare everything true, right? You're never gonna, you say all results are positive, that way you're never gonna miss a true hypothesis, but you're also gonna have tons of false positives, right? So it takes effort to find the true things and not call the false things true. Right? This is sort of classic signal detection theory. And in the model, we assume that effort must be exerted to do so. And increasing effort also increases the time it takes to produce new results. You have to run more subjects, do more careful analyses, etc. Novel negative results are tougher to publish than positive results. These are all assumptions that we make, and we think we're pretty reasonable. Finally, we assume that labs that publish more are more likely to have their methods reproduced in new labs. So this is like attracting grad students and postdocs and placing them in good places, or being famous and influential and having your methods copied by others. The model has two phases, which we call science and evolution. Walk you through them. So in the science phase, right, this works pretty much just like the previous model I showed. There's a process of hypothesis selection, which we just assume a background base rate of 10%, which we think is actually pretty optimistic. Before that. So this is the graph here of the probability of conducting a new study as a function of effort. This is the kind of the way the model works. Then there's the investigation period. This is a graph of how power and false positive rates are linked. As power goes up, false positive rate goes up, but effort changes which curve you're on. So that for the same amount of power, you can have a false positive or a lower false positive rate if you exert effort. Finally, there's communication, in which novel positive results are always published and negative results are difficult to publish. Yeah.
Sorry, I might have missed this, but what are you defining effort as?
Yeah, effort is a fundamental trait of each lab in this, and it directly relates to the probability of being able to conduct a new study at the beginning of a time period, and how and what the false positive rate is for a given level of power. And so it is just an intrinsic part of the methodology of a given lab. So the best methods in what we sort of idealize as science, in doing the best science we can, would be to have very high effort, and therefore to allow us to have a high power while minimizing false positive rates. Yeah?
Are all of the agents, or all the labs, like non-error rate for getting true or false hypotheses the same? Or?
Yes, all labs, yeah, the assumption here is all labs are equally good at choosing hypotheses, which is obviously something that actually goes, but yeah, for the sake of the model, we assume that all labs choose hypotheses, and 10% of all hypotheses chosen are actually right, and 90% of them are wrong. Yeah, Chris.
But this probably fundamentally varies to the extent in which you're doing kind of incremental science versus trying to take a big leap, right?
Totally, it totally does.
So I mean, it's certainly fair to sort of, let's just put it at point one, but first of all, I just want to make sure I understood that, right?
Yes.
And in some sense, and it's interesting, and maybe you're going to come up to this at some point, but funding agencies in some sense also tend to push away from the incremental science. Sometimes, maybe I'm stealing thunder.
No,
I find that really fascinating.
So I'm not going to talk about funding agencies here, but the project that I'm working on now with Pablo is on basically bringing in funding agencies to
Okay,
involve like
yeah, very
to its offspring lab, and that offspring lab inherits the methods of its parent lab with some variation. There's some sort of mutation, so it changes it a little bit. All right, so what happens? So paper was called The Natural Selection of Bad Science. We can do a couple of experiments that are kind of simple. Let's just hold effort constant and let power evolve. Well, power just evolves to perfect because if you're trying to get a lot of publications and positive results are rewarded, you should just call everything true and send them all in. Obviously, let's see these other lines that the light blue is the false positive rate and the dark blue is the false discovery rate, the proportion of published papers that are wrong. This is obviously pretty unrealistic, right? You can't, first of all, no one would let you just submit, send in a ton of wrong results, and it's pretty much impossible to get away with 100% power for a variety of reasons. I think it's a little bit more realistic to hold power constant because we do have some measures of power, even though they're imperfect. But effort is a lot harder, and false positives are a lot harder to detect, to know what the rate is. So let's see what happens if we hold power constant and allow effort to evolve. And what happens is effort plummets, right? Scientists are rewarded for producing lower and lower effort, and the number of false discoveries in the literature skyrockets. I agree that this model is unrealistic in a lot of ways, right? But I think that there's something to be said for this, looking at it with this simplified kind of dynamic, because if we assume that there is selection for the best quality methods, for the ones that produce the highest quality and most rigorous science, we should observe increases in our methodology, improvements in our methodology. However, if this force is at work, we should see minimal, no change, and possibly things getting worse. And the extent to which those directions balance each other out is sort of the extent to which this effect is working. So in 1967, Paul Meehl, who's a philosopher and psychologist, published this paper in Philosophy of Science, Theory Testing in Psychology, and he, comparing theory testing in psychology and physics, he was very much criticizing psychology and said, we don't understand p-values here. People are using p-values all wrong. They're using them as if they're the probability that your hypothesis is incorrect. That's totally not right. You should use it better. In 2016, the American Statistical Association published their statement on p-values saying, you guys are all misunderstanding p-values, you're using them wrong, you're using them as if they're the probability that your hypothesis is incorrect, you really should stop doing that. Look, this is from their statement. Let us be clear, nothing in this statement is new. Statisticians and others have been sounding the alarm about these matters for decades for little avail. So for 40 years, 50 years, people have been saying, you're using p-values wrong, this is the right way to use p-values, statisticians have all agreed, and the methods haven't changed. In 1962, Jacob Cohen published this paper on statistical power, sort of introducing the concept of statistical power, saying, guys, psychology is going to be full of false positives for running all these underpowered studies. Right? You need larger sample sizes, you need more careful analyses in order to correctly test your hypotheses. In 1989 and 1990, a couple of papers were published sort of saying, well, okay, in 20 years since Cohen's paper, has there been an increase in this power of psychology studies? And they came to the conclusion that no, there was not. So Richard McElreath and I updated their data to go up to 2014 and found no increase. So all these data points are reviews of power in different subfields of the social sciences. And this is the power to detect small effects, which is the size of most effects in the social behavioral sciences. So about 0.24, which is pretty low. If you don't buy this, Zucks and Ioannidis just published another analysis of 100,000 statistical tests from 10,000 papers in psychology, cognitive neuroscience, and medicine from a 4-year period, and their results pretty much in line with us. The power to detect small effects on average in psychology and medicine is 0.23, pretty close to what we got. In cognitive neuroscience, 0.14. So it's pretty bad. And cognitive neuroscience has sort of been getting a lot of flack recently for having very, very small samples and using very giant data sets where they can sort of mine for effects. So what do we do about this? There's been a lot of talk about replication and the importance of replication. There's a EBS paper open to commentaries right now about how the importance of replication in behavioral sciences, but in really all sciences. Right? So a number of papers have come out talking about the importance of replication. This was kind of adorable. This was a paper, an editorial in Science Translational Medicine, proposing that when you submit a paper, you sign a pledge saying if somebody fails to replicate your study, you should pay a fine. Right. I think it's a terrible idea, but it's one of the only concrete ideas. So we were like, let's test it. We can throw this in our model. We'll add replication, and in the model we can say, well, labs now, in addition to testing novel hypotheses, will add some rate R. Each study will be one that's already been published. Retesting something that's already been published. We assume all publications are publishable, whether they are positive or negative, and convey 50% of the prestige of a novel finding. So in the previous model, or the previous version, imagine that every publication of a novel finding gets you 1 prestige point. Right? So replication gets you half a prestige point. It doesn't actually matter what it is as long as it's more than 0 and less than 1. If somebody else replicates your study, you get a boost in prestige. Why not? And you get a 1/10 of a prestige point. And to make this as sort of in favor of this working as we could think, we said, all right, if your original study fails to replicate, you lose 100 prestige points. So you lose the prestige that 100 novel papers would have gotten. It's really terrible if somebody fails to replicate your paper. So what happens in the model? All right, it doesn't work. When we started it with 1% replication rate, which is, at least in psychology, what some estimates of the replication rate actually is, we found that replication overall increases a little bit, but in general, people can do better by just having worse methods and publishing novel findings. We thought, well, maybe it's just the replication isn't increasing fast enough to counteract this effect. So we stopped letting replication evolve and just instituted very high replication rates, 25% or even 50%. What if like half of all papers are replications? Maybe that'll work. It doesn't work. It slows it down a little bit. Right? But here's effort evolving with 25 and 50% replication. And the reason is that, yeah, a lot of people here are going to get slammed, but you can't replicate everything. And the best performing individuals will still be those who can decrease their effort and publish more papers. So, some take-homes from this. Incentives to boost quantitative metrics can lead to the degradation of research methods. This requires no fraud or ill intent. That does happen. Fraud totally happens, but you don't need fraud for these incentives to be bad. Only that successful individuals are transmitting their methods, and that success is linked to these quantitative metrics that can be gained, whether intentionally or not. And this is I want to stay on this for a second because this is a kind of cultural evolutionary perspective here. You can imagine that something that can be transmitted is misunderstanding of methods. If somebody doesn't understand p-values and is rewarded for not understanding p-values, then there is an incentive to misunderstand p-values. And the ones who do will produce lots of literature that making big claims that get rewarded, and those misunderstandings will get promoted. The individuals who do understand it and are yelling in the back of the room saying, no, that's not right, they're not producing as many high-impact papers, they're not getting as many grad students, they're not placing their grad students as high, and so those methods aren't getting transmitted. changing individual behavior is not enough. That's what this means. Right? Improving science requires some institutional changes. It means that the rewards have to change. This is unlikely to be easy or happen quickly, but some promising changes are already happening. There's a lot to be said about this, and that's sort of for another presentation, but I want to very quickly talk about some of those. Right? So, DORA, which is the Declaration on Research Assessment, came out of a biomedical group in San Francisco, a big meeting, and talking about the need to improve incentives for science. The journal Nature and Science have sort of adopted, at least on paper, some of their ideas. Things like, try to reward papers for quality of methods rather than sort of novelty of findings. Places like the Center for Open Science, I think, are doing really important work promoting preprints. I think promoting preprints is really important, not only because it gets work out and helps to share work, but also it sort of takes away some of the prestige baggage from getting a prepared paper in a high-impact journal. If you have a preprint up and people are paying attention to it, who cares where it ended up getting published, right? There's a nice organization that just sprung up in the last year called Bullied into Bad Science. And I wanted to highlight this in particular because it's really directed at early career researchers. This is a sort of, basically a collective with the express purpose of allowing early career researchers, grad students, postdocs, and young professors to sort of form a support network. Say, we're not going to be bullied into doing bad science. If your PI or your collaborator wants to get you to publish something that you don't think is best practices, then this is a sort of support network to help you stand up to them. Okay? It also means when you guys go throughout your career, pay attention to these things. When you're looking at who to hire, who to work with, what kinds of organizations you want to associate yourselves with. These things are becoming more and more important. And I think that there's a lot of, there's more things like this coming up all the time. I think people are paying attention to the problems in science in a lot of different fields, and things are getting better. So I want to end with the fact that science is still awesome. It really, I think it's a really awesome job to get to do science. You get to, the world is so overwhelmingly confusing and magical, and to be able to spend your time trying to figure out how even a part of it works is amazing. And if you do good science, then you can actually learn something true. And I think that's better than tenure. Well, the tenure is sweet. We've done it for it. But there's when I was in high school, one of the books I read that kind of really got me excited about science was Richard Feynman's memoirs. And he sort of famously said, the first principle of science is you must not fool yourself. And you are the easiest person to fool. Done with that. Thanks. Looks like we have a lot of time.
Yes, that's good. Alpha.
Yeah, so if you go to going back to like the prestige in the model, if you change the kind of the ratios that you get from prestige, that doesn't make a big difference.
Oh no, it does, as long as the replication is worth less than a novel finding, the exact value doesn't matter. It can be 0.95, it can be 0.05 for a replication, as long as it's worth something, but less than the value of a novel finding. It will also depend a little bit on the strength of publication bias, though. I haven't presented a full analysis. I will note that the source code for the model is on the journal webpage, so if any of you want to play with it, it's in Java, and go nuts.
So I teach the Psych Science Pro Center for first-year students, and we were just talking about the publication process, and one of them asked me what I thought about the open science movement. I mean, whether I thought it was gaining steam, and whether that was something at the graduate student stage of the game you should be participating in, and I was really, found it a hard question to answer. So now I'm going to throw it at you.
It's a hard question to answer. Because I do think this is gaining steam. And I think there are an increasing number of people who care about this stuff. And as time passes, they will end up getting into positions of power, hopefully, and being able to affect more things. So my colleague on the paper, Richard McElreath, at the time I worked with him on this, he was a professor of anthropology at UC Davis. He's now a director at the Max Planck Institute for Evolutionary Anthropology, so he gets to hire tons of people, and he just flew an ad and explicitly said, things I don't care about, H-index, impact factor, number of publications, things I do care about, open science, math skills. So, he really did write math skills. Max Planck is a lot of age, but I'm hopeful. But you're right. I mean, the other side of it is that not everybody hasn't reached it, and there are definitely people who look at things like number of pubs and impact of pubs, and they use that in decision making, even if they sort of know in their hearts they shouldn't. It's hard, right, to evaluate tons of people.
Yeah, it's like GREs with grad students.
Yeah, it's a low quality signal. It's the question is whether or not it's a valuable signal at all. Maybe if you don't know nothing about two researchers, and you see one has a bunch of pubs and one has no pubs, knowing conditional on no other information, probably the one with a bunch of pubs is going to be on average the better one. But if you have their papers,
You should read them.
then you should read them, right? And then conditional on the actual papers, then the number of papers is pretty low information. When I remember talking when I was a postdoc, two things, like two stories come to mind. One is I remember talking to someone who was in a molecular biolab at Berkeley. She was a postdoc, and she said her department was hiring, and the way she heard it, their department wouldn't even look at somebody who didn't have a paper in Nature, Science, or Cell, right? Which is just like tragic, given how noisy the rate. Like each of those journals accept like 3% of submissions. So, and we've all read crappy papers in Science and Nature. So,
Lots of failures to replicate.
yeah, lots of failures to replicate, and things that you're just like, But. And tons of amazing papers that get, that like you can't communicate in 3 pages, right? So I think that's really too bad. When I was in my first postdoc, one of the other postdocs in the group came up to me and he said, we need jobs. It's like, I know, we do. It's like, it would really help our careers if we get a paper in Nature. And it's like, yeah, that's probably true. And he said, well, I think what we should do is think about like what we could do that would get us, like what's a project we could do that would be most likely to get us a paper in Nature? And I was like, no. Okay, like, no. We're gonna stop talking about this right now. But I think it's like people do this, right? People are like, what are the kinds of not what's the thing that's most important to know, or what's the thing that I'm most passionate about, or what's the thing that's going to get me a paper in a journal, and I think that's like a tragedy. But I also recognize like we got to eat, so it's tough. I don't think there's any simple answers.
There you go.
So I was just wondering about the scale and applicability of these groups in actually like open science, and actually having a positive effect on the incentive mechanism. And so the thing that it made me think of was in the blockchain space, there's this thing called a decentralized autonomous organization or company. It's basically just like, the whole point of it is to realign all incentives of all parties involved. So like, rather than Uber being like a whole bunch of people that are users, and a whole bunch of people that are stakeholders, and then a whole bunch of people that are like company people developing the product, that all have completely separate incentives, they kind of just tokenize the whole thing with a coin, and then all those people are the same people. So in either case, if you're a builder or a user, you're also an owner. I know that the science space is not quite as amenable to like maybe some of the highly volatile economic things that happen in that sort of space. But I was just wondering if you think that, well, first, how well do you think those groups that are currently attempting to do it are actually achieving this goal of like scaling? How you mentioned how difficult it is to actually do a good job of curating that information, and whether or not people are looking at, there are like dozens of projects that are trying to do this in the blockchain space. I'm wondering if there's any overlap or.
Yeah, I'm not really familiar with what's going on in the blockchain world, but
we should talk about it.
yeah, this is the second time this week and never before that this is brought up to me. So yeah, I'm happy to.
Was it Laura Kelly?
Yeah, it was Laura Kelly.
Yeah, good process that.
I think, yeah, I mean, a big corporation can be centralized and can make centralized decisions in a way that a more dispersed, sort of acephalous organization like academic science as a whole has more trouble. So, I mean, this is good, right, because you can get sort of pockets working on totally unique different things and then coming up, being like, hey, look at this, you didn't even know you wanted to know this. But it's also difficult, right? Because if you have centralized power, then you can say this is the new rule, and we can do it this way, which obviously can be good or bad depending on how good the rule is. I think so. I don't know that much about. I don't have that much to say about that aspect. About how more generally how effective these organizations are being. I think they keep gaining traction. I think they continue to gain traction. I think the Center for Open Science is the biggest and most influential of these organizations. They've been able to get a fair amount of grant money, and they have some very true believers working there who are working really hard to get out the message and to push for these things. They have instituted incentives for replications, cash incentives actually for replications, which are mixed feelings about, but it's people are continuing to value replication more and more. I see that, especially at earlier career stages. I think that what was I going to say? They've been doing an amazing job with organizing preprint servers recently. So physicists and computer scientists have been using preprints for decades, archive. Other sciences, not so much. And some social scientists, mostly economists, they used SSRN for a while. That has been losing face recently ever since it got purchased by Elsevier. But some new ones have sprung up. So in 2014, I think, or 13, bioRxiv started, which is a preprint server specifically for biology, and they've been gaining a lot of submissions. And just recently, a whole new one, a bunch of new ones, a lot of them organized by the Center for Open Science, has sprung up. So SciArchive, SocArchive. There's ones for marine sciences, chemistry. I think there's even a COG archive. There's an Earth archive. It's a bunch of these like blank archives. For those confused by the way archive is spelled, the capital X looks like a Greek letter chi, and physicists are hilarious. So I actually think preprints are really important for this because it democratizes a lot of science, and also I think takes some of the burden off of reviewers, which would become sort of de facto editors. Like a lot of people, I've seen submissions where the paper's clearly not ready for publication, and people just sort of assume, well, it's going to get a revision anyway, no matter how good I do it, so I'll just submit a kind of half-assed version, and they'll tell us what we need to do. I don't, it doesn't happen all the time, but people do it. But if you submit, you have to submit a preprint, then that's going to incentivize the original submission being better. And if the data is open, that's going to hold people accountable. And more journals and funders are incentivizing open data. So the Wellcome Trust in the UK now requires all grantees to submit their data and to post, I think post preprints and to submit to open access journals. The Gates Foundation, all data has to be open, all papers have to be submitted as preprints and made open access. So those kinds of things I think are going to help. So you know, I'm optimistic cautiously.
So that answered like one and a half question I had about like the ownership and properly influencing like false positive rate submissions and results. The other part is, I wonder to what extent, moving back to single authorship papers, how much that might actually influence this growth in false positives. Because then, like, you are the only one accountable for it not registering.
Yeah, that's a really interesting point.
Can I add a quick addendum to that?
Yeah.
Is there a higher rate of some sort of like truthiness when people working together?
That's an interesting question too. I don't know. There is some data, going back to the earlier thing, there is some data, or there, I haven't gone through it yet to sort of look at the analysis, but there are some suggestions that higher impact journals have a higher rate of false positives than lower impact journals, or at least sort of mid-level journals, because of this sort of selection for novelty. In terms of the single author, I think the single author thing being accountable is a really interesting idea. There are clearly some science that requires collaboration. And I think collaboration is awesome. I mean, some of my favorite projects that I've done have been working with other people. It's fun to work with other people and you get good stuff to work with other people. So I don't want to say like you shouldn't collaborate. But there was a point, I just was reading a blog the other day that made an interesting point about the sort of like out of control authorship in some fields, or what some people call out of control. Like there was a physics paper, there was a particle physics paper that came out last year that had 5,000 authors or something like that. It was, you know, it was like, there was like a 24-page manuscript and something like 13 pages of them were authors. It's just the author list took up 13 pages.
One author per word. I wrote one word.
And you know, the point is like, okay, this is a really collaborative thing. Like, you need someone writes this piece of software, someone writes that software, somebody got that data, somebody worked at this thing. This is a multi-year process. There are tons of people, and if there's no way to reward the people who worked on the project, other than with the paper, then you got to put them all on the paper, even though most of them had nothing to do with actually writing the results up or analyzing the results or coming up with the argument. They just were people who helped you collect the data. It's a rational response to incentives for rewarding just publications. If we can figure out other ways to reward things, that would be good. Right? If we can reward effort spent writing, if we can reward time spent working on a project and say this counts, the fact that you worked on collecting data when you go and you look for jobs or go out for promotions or try to get grants to say, I've been working on this thing even though I haven't written any papers, that would be, I think, a step toward progress. So yeah, both sides. I mean, some papers you gotta collaborate with. So it's not, I don't think there's anything, certainly not, I'm gonna say there's definitely nothing wrong, per se with multi-authorship.
But it's interesting, the authorship issue. Two issues. One, that it's actually allowing you to limit your effort or lower your effort, right? You're distributing it across authors. And so because it doesn't cost like it used to, that's a good way to limit effort or to reduce your individual effort. But in the past, this was a factor in whether you would get tenure. What was the average number of authors? And, you know, it still is to some degree, but less that and more about where you are on the authorship lineup.
Yeah.
But I see what has happened is, you know, I'm old enough to have been around when these arguments were happening about order of authorship and whether senior author last counted in psychology. That used to be not acceptable in psychology, and now it's like the default. Why? Well, because more rewards to hand out, right? You have the first author position, the last author position, and now those people are tenured and full professors and making decisions, and it's like out of control, the authorship thing, because there's nothing to tamp it down. Which is actually very interesting.
Yeah. When I worked at, I guess, could say another unnamed university, but there's not too many options. So it's just Hopkins. It was in the med school, and they had, like, I wasn't in faculty, so it didn't really affect me, but I'm talking to faculty. There was like a formula that was literally written out that was like, this is how much first author paper counts, and this is like how many first author with X number of co-authors, or a last author paper. And if you had third author on a paper with like 5 authors, that barely counted for anything. Which is a way of, I guess,
that's trying to control
we
tried to come up with these things.
But there's also these weird things in medicine where people will get, like, they'll be like, they'll say, can you take a look at this paper and just like read it over before I submit it? And I literally saw this happen a bunch of times. They're like, yeah, if you make me an author, I'll totally read your paper. I'm like, that's insane, but it happens.
Well, so I had a student in ProSem ask me, what about acknowledgments in papers? Which at first made me laugh, and then I thought, oh, that does kind of ring true, because, you know, I've been acknowledged in papers and not because
Right.
nobody gives a shit, right?
Yeah, it's nice to be acknowledged.
It's courtesy.
It's nice.
It's not like, yeah, it doesn't.
Incentivized.
I think it actually does matter a little bit over time, because if you see the same names over and over again in an acknowledgement, it can actually.
That wasn't what I ended up saying.
But yeah, but you're right. I mean, it's not like you can be like submit a tenure package and be like, I was acknowledged in 10 different papers, which, you know, I mean, I think the UC should count preprints, for example, for merit review. It doesn't.
So talk about preprints some more, because that's something that I don't use. Like
Okay.
what?
So I just wrote a blog post on preprints that is going to be published for a blog called Academic Life Histories. It was, they asked me to do it. So I'll send that around when it comes out, which will be in the next month or so. But I can send you the text of it if you want. But so does anyone here not know what a preprint is? Okay, a few people. Okay. So preprint is the paper before it's published, before it's been peer reviewed. The idea is you did science, you wrote a paper. You haven't gotten it through a journal, but you still want to share it with people. There are preprint servers, Archive, BioArchive, Blank Archives. The Center for Open Science has a thing on their website with like a whole list of all the archives, all the preprint servers, and you can search them all as one thing. It's very cool. But it's basically, you're putting up the paper before it's been peer reviewed to say, I did this, and I stand by it. And you do it for 2 reasons. One is you say, well, you know, I'm going to solicit feedback. I would like, if anyone has something to say about the work I did, it would be nice to get that. And the other is to say, I did this work, I think it's good, and check it out. Anyone who's gone through peer review a few times knows that peer review definitely doesn't catch all the mistakes. And knowing that something's been peer reviewed is only kind of a minimal threshold anyway for quality. I think there is, well, I'll say this in a second, but there are a bunch of problems with journals. I think journals are really good. They take a really long time. I think things can take forever to get reviewed and published. They're really fickle. There are costs involved. There's access. Not everything is open access. Things that are open access have article publishing fees. And preprints sort of get around, and there's the whole sort of emphasis on prestige. So I'm sure if you're an editor at Science, you're getting deluged all the time in submissions. If you have a paper and you want people to see it, put it on a preprint server, and maybe we'll look at it. And more and more journals are allowing you to cite preprints. More and more funding agencies are allowing you to cite preprints now. The NIH now lets you cite preprints. The Wellcome Trust allows you to cite preprints in your grants. And you can point to a preprint and say, look, this is work that got done. I'm using it to do my own work. And a lot of, they're time-stamped, so you don't have to worry about anyone stealing your work.
Oh, that's what I was saying.
That's what I was going to ask too.
Yeah, all of them are time-stamped. Some preprint servers even give you a DOI for the work. So you can say, oh, well, this paper came out before your paper did. And you say, well, I put the preprint out before that paper came out. So it actually,
So it's basically like,
So
in terms of getting good feedback, that's much more effective.
To me, there was a study done recently showing that only 10% of bioarchive papers got unsolicited feedback. That said, bioarchive is especially nice. They have a very nice kind of simple comment thread kind of thing where people can do comments. The Center for Open Science preprints do have stuff like that too, and all of them you can not only put up your paper, you can put in supplementary materials as well, data sets, etc. There's a paper recently that it came out and I was like, I think this model might be problematic. They had put up the model code on the Center for Open Science listserv, so I was able to look at it and run it and actually figure out what they actually did, which is really nice. So to me, I think there are very few reasons not to use preprints. I think if you're doing like certain medical stuff, where it's really important not to be wrong, there might be reasons not to use preprints, or if there's a really, there's a result that you just can't chance it before it's gone through peer review maybe. But also, most journals now, it used to be that some journals wouldn't let you publish if it had been previously published and they would count preprints. It's not the case anymore. Even Nature and Science, NRT-ias, all of them allow you to post a preprint and still, as long as it wasn't published anywhere else, you submitted it to a preprint server, you can submit it to Nature and say, yeah, it's been up on a preprint server, but nowhere else. Yeah, Chris.
So I love it. I have tons and tons of questions. I know we only have a little bit of time, so I'll do maybe a couple of highlights. So one is, we have some people who are engineers here, of course, and I think about engineering papers that don't have p-values, and not just engineering, right? There's many areas of science, applied math maybe, where maybe I don't. So now, are they immune to this? And if that's one question, and if they are, if something different, how would we compare the progress and the culture in an area where you're not worrying about p-values? Is it help us sort of understand as a contrast for everything that you talked about today?
Yeah, well, I think
you're not doing statistics.
It definitely doesn't rely on p-values. It can be anything where there is some sort of threshold or even some sort of calculation as to whether or not a result is read or not,
right.
And especially if it's in a field where certain types of positive results, let's say, are easier to publish. And that has to do with prestige of publications too. Not every field cares that much about how much you publish or the extent to which the model applies, I think, totally varies by field.
Yeah.
And we talk about this explicitly in the paper. And it's really the extent to which you think this applies is the extent to which you should be worried. There are some fields where, I'm familiar with a very select and kind of probably very biased sample, but most physicists I know don't care that much about journal impact factor. They don't care if they get a paper in Nature or physical review letters. They care about, do people notice and do people notice their work?
Mm-hmm.
And is it good?
Mm-hmm.
And I think that's awesome. There's an interesting, it's not really answering your question, but there's been this interesting thing that's sprung up mostly in physics, which are these like wrapper journals, which are basically like, they're based around preprint servers where people will post a preprint, and then the journal is just like submitting your paper to the journal is just sending the editors a link to your preprint. They review the preprint as it's on the preprint server, and then they link to the preprint from their website that's accepted to say, this has passed our peer review.
Well, this is what I was going to ask. This is like what you're describing as a way to circumvent the whole publication system, which wouldn't be a bad thing.
Right.
Yeah. I mean, I think that journals do serve a really potentially important function.
Mm-hmm.
Like a lot in curation, right? Like there's so many papers out there. If you only have preprints to go through, then you can't read every paper on a topic, especially if it's a hot topic. And using information, like a journal curates and it collects certain kinds of paper, it creates a community around that paper, and it tells you also like what kind of paper you're going for. Also, I do think that and we've all experienced this, those of us who've gone through peer review, editors and reviewers often make our papers better, right?
Sure.
Sometimes you submit something and a reviewer is like, it seems like what you're talking about is really related to this other literature that you didn't know about. Oh, wow. Or it'd be good if you did this analysis and you learn new things or you come up with a better framing by doing that. So I think it's all, journals serve a really important function when they build up a reputation for having quality. I think society journals or, field-specific journals tend to be better at this than sort of tabloid journals. If there was a paper on evolutionary theory and it came out in the American Naturalist, I would be much more likely to buy it, to believe it, than if it came out in NRT-ias. Because I've seen review at both those places, and I know the American Naturalist is really, really rigorous, and all their reviewers are deeply steeped in theory, and NRT-ias is kind of a crapshoot. So, question.
I don't know how popular this website is, but I bumped into it the other day, and I really like the idea of it. It's you could submit the work that you're working on, or maybe even a preprint, or something that's not even complete yet. You submit it, you can recruit people who are in the field already, established, tenured, and have published a lot of papers. You recruit them to be potential reviewers. Okay. And as you're working through it, they'll send you a review on your work currently, and it'll be publicly available. You can see what's going on there. The website is called F1000.
Yeah, okay, F1000. Yes, F1000 also has a preprint server and also does what you're talking about is I think called registered reports or pre-registration.
Yeah.
And this is, I didn't mention this, but this is another thing where, you basically submit your research plan. You say, this is the study I'm going to do. These are the analyses I'm going to do. And you can get them reviewed. And then, when you submit your data, you can say, well, the plan, these are the aspects of the plans that were pre-registered and that were reviewed, and then we did these other things that weren't pre-registered. And the idea is that this helps control for false positives, like multiple comparisons and things, where you say, these were the things we were planning to test, and therefore we had motivation to test them, and we weren't just sort of data snooping or trying to p-hack. I think it's really valuable. It doesn't, not all fields it makes sense for, but if you, the work I do is pretty much all modeling, so it doesn't really make sense to pre-register my work. But I think if you're doing a study with sort of fairly straightforward data collection and analyses, I think it's...
Yeah, it seems like it works in where I'm going for, because right now I'm collecting data to develop a model eventually. And it seems like just to post it maybe in there, see what my strategy is, collecting data, see if it's good enough to continue, and then see what I think.
Yeah, and so it serves the dual function of, one, you get professional feedback from outside feedback on your research plan before you do the study. And then also you can sort of stand a little bit more confident in the analyses when they come out in a certain way. You say, these were, I did the ones I was planning to do, and it came out this way. So this wasn't just like, when you, as a reader, it sort of instills a little more confidence in the analysis.
I also like that there's a rating system for papers, paper 21.5.
Okay. Yeah, I haven't looked at, all right, let's go.
So the pre-registering and pre-paper thing reminds me a lot of what happened to me as soon as I got here, which was like, oh, I have a hypothesis. How do I like record it so that I don't trick myself into thinking, you know, that I had a slightly different hypothesis later?
Yeah.
And my answer last year, because I didn't really know about this stuff until like almost the end of last year, was to just put it on GitHub. And you mentioned that physicists and computer scientists are the ones that kind of were, I don't know, leading the charge in this. And I was wondering if they are still commensurately ahead, and whether or not you think that that has to do with the fact that they basically are the fields that use public repositories in the first place, so that they kind of are open to this mindset.
The latter thing I think is probably true. I don't know for sure, but my intuition is that it is. As far as whether or not they're still leading the charge, it's hard to say. I think I kind of feel like they peaked a little bit to some extent, and so now everyone else is catching up. So the fields where there's the most change happening is not physics, right? It's probably biology and psychology. But I think that, like in a lot of ways, you know, physics is sort of the science, right? And so people look to physics for sort of inspiration in a lot of ways, and this is one of them. Chris.
So I'll try to segue from that. I mean, in a more mature field, going back to your model, because I want to ask a question about the model, and I know it's pretty much time, but maybe we can do this last one. In the model, you know, you got the base rate, and you set it at 0.1.
Yeah.
So, and I mentioned this idea, well, you know, some labs are doing more incremental work where I imagine their base rates might be higher than a lab that's doing more pioneering work or something like that. So now, if you take that up to a sort of larger scale of a field, could we say that physicists probably have higher base rates in the sense that they're a more mature field, it's more incremental at this point, they're not looking for these big giant sort of leaps forward type
I think
of
that's
thing.
absolutely true.
Right? So that's something I think, you know, important to sort of think about.
Yeah.
Just want to, you know
No,
that.
I agree. I mean, I think there's two. One thing I didn't talk about is like, I think, you know, one of the things that physics has is very, very strong theory.
Yeah.
You know, I mean,
Yeah, and that's very
you
important.
can't test you don't do an experiment in physics really unless you have a theoretical prediction.
Yeah, they're not taking shots in the dark.
Yeah.
So my other question was then, now this was the question I really wanted to ask was, so in the model, have you, and I'm sorry if it was in the paper and you just didn't mention or I missed it, did you try a model where you vary the base rates and are some base rates selected for and others not? Obviously my thought is that the low base rates are going to be getting selected for, but maybe that's,
Yeah.
I don't know. Yeah.
So the short answer is in the first paper where we didn't have labs competing, we just varied the base rate to population wide.
Yeah.
And it matters a lot.
Sure.
But in terms of selection, we didn't include it in the second model, in part because it just seemed like too many moving parts to analyze.
Yeah.
I will say though, in the sort of next generation model that we're doing, which is sort of in the works now, we are going to do that.
And I'm not surprised because again, coming from NSF, I can tell you, you know, this whole thing about being transformative is like a huge pressure on the low base rate stuff, basically. I mean, like, very explicit, very, very explicit.
Oh, absolutely. So I mean, the project that I have going now is a small grant from DARPA, and they were like, as funders, we would like to know how we should allocate our funds. So what kinds of funding models we would select for, you know, different kinds of science, and you know, the kind of thing that this model can really focus on is things like false positive rate, less so on innovation or transformative things, but we can include things like varying base rate, which we're going to do.
I think they're correlated, but anyway.
Yeah.
Any other questions? Let's thank our speaker again.